So let's kind of like remember where we were. I'm just going to keep going with the stuff. So last time, I think I gave you an explicit description of the tensor product of two modules. And then we showed this neat trick. So last time we kind of did two neat tricks. Right, we did this one that M R mod I is due to this M mod IM. We also did M if we localize. This is the same thing as the localization. And then this implies S inverse of R was a flat R module. Okay, so it's a ring, but you can view it as a module. That's because localization respects exact sequences. So like localization like commutes with everything. It's super nice. Yeah, and so I'm gonna continue with more tensor product stuff. Great title. But let's just continue. Okay, so let's do a theorem. Theorem, lemma, whatever, theorem. Okay, so finitely generated free modules are flat. Then M is a flat R module. Okay, so what is flat? Let me just kind of remind you what flat means again. Flat means it takes, after tensoring up, it takes injections to injections. Okay, so that's all, I guess, all you need to know about flatness. I mean, so sorry. So the tensor product. So you get the surjection part for free because it's a left adjoint, and then you need to check injections. Okay, so what I'm going to use this is, so I guess one of the other things that we've been talking about is like how we state some of these properties about commutation of Halms, like with direct sums and things like this, and how we need them to be functorial. This is another example of where we need functoriality. Let me go back here. I think I wrote down some basic properties here. Okay, so these are important. Okay, and so in this example, I'm gonna do I'm gonna use the way that it distributes over direct sums, and then I'm also gonna use the functoriality of this, I believe. Okay, so let me just go back here. Okay, so proof. Okay, so suppose let's see. Let's suppose V prime to V is an injection of R modules. Okay, so what we get to do is we have this. So what we'll do is we're going to take the tensor product of this. So V prime direct sum or tensor product over R with R to the n. Okay, and then this thing here goes to V tensor product over R with V. Or sorry, not with V, with R to the n again. And remember, R to the n is R direct sum with itself n times. Okay, so this is so this thing here is V, and then now I'm going to do, this is R direct sum R. This is n times. Okay, and so by induction, I guess you can prove that tensor products commute with with, you know, a finite number of direct sums, okay? And similarly, this thing is isomorphic to V, or just, I should say, distributes over. Okay, and so now we have that this thing here, so this is naturally equivalent to, and this thing's naturally equivalent to, this is V tensor R over R, or V prime, direct sum V prime tensor R over R. Okay, and this one is V tensor R over R, direct sum direct sum V tensor R over R. So what it is, I distributed the tensor product, and I'm using that these things are naturally equivalent. Okay, and so then we get, so what are these things? So now I can use the cancellation property, right? So we have two R's next to each other in all of these. Okay, and so this thing is isomorphic to V prime direct sum V prime, and this happens n times. Okay, and this thing is similarly isomorphic to V direct sum V. This happens n times, right? And so this is V prime tensor n. This is direct sum n times. And the map here, okay, so do we give this map a name? Let's give this map a name. Injection. A good name for an injection is J. Okay, so this is J tensor R to the n over R. So we're just applying the functor to the map. And it turns out that that's naturally equivalent to J tensor n. So it's a direct sum of injections, which is an injection. So this is a direct sum of injections, which is an injection. Okay, there we go.
What's the difference between the notation of R to
They
the
put like a
n
0 on the
versus-
left. Are you probably
So what's the difference between the notation, or I think you're going to say this, R to the n and R to the n, R to this thing?
Yeah, exactly.
They're the same.
Got it. Thanks.
I only do this to emphasize that it's a direct sum sometimes. Yeah.
Taylor,
Yeah.
follow-up question. So maybe I'm totally misunderstanding something, but this is going to imply that like Noetherian things are flat.
Noetherian things are not in general flat. There's lots of Noetherian things that are not flat. It's just about free modules. So it said this is the statement that free implies flat.
Okay.
So I'm kind of building up. Let me give you kind of a spoiler. Okay. Let me give you a spoiler. Okay. So here's the spoiler. Okay. So we have. Let me just say what we have so far. I'm building up to something. So we have that free implies flat. We just proved this. And we have free that implies projective. Okay. The spoiler is that projective implies flat. Okay. And it turns out that over a local length, so if you have a finitely, and then there's kind of a big theorem. So over a local ring, a finitely presented module if M is finitely presented, Okay, so that means that it's finitely generated and that the kernel is also finitely generated. Okay? So there's like that exact sequence thing. Remember, we were using those exact sequence when we did modules over PIDs. And we did like Smith normal form and that sort of thing. Okay, so if M is finitely presented, then M is free if and only if M is projective. If and only if M is flat. So in this case, locally, all these notions of projective, flat, and free, this is the way you should think about it, right? Is that over a local ring, essentially all these things will collapse, right, into one notion. Okay, and so it'll be very useful to like take modules and then localize them, and then we know what flat and free look like locally, and they look like projective. I mean, they look like free. Free modules are easy. Free modules are very easy. They're like vector spaces, right? And so we want to make things look like vector spaces. Yeah, that's kind of the name of the game. Actually, this is what this tab was. All right, so this is the Stacks project. Okay. All right. But we're not there yet. But we did show that flat or free modules implies flat. So that's what we just proved. We proved free implies flat. Okay. All right. Okay, so let me give you some cool stuff now. All right. Where is my? Okay, so